Take a minute to read the question and understand the question. Okay, I hope everyone has read the question. Now let us discuss what exactly they're asking us to find out. So there is a pipe, and from this point onwards, the pipe is porous, which means material can enter and leave the pipe. So over here, this is x is equal to 0. And this point is x is equal to L. So the distance between x equal to 0 and x equal to L, it has a porous wall. And fluid is entering into the pipe from this porous wall. And the flow rate at which the fluid is entering is Q into x by L whole square. This is the volumetric flow rate per unit area. So this is the volumetric Q by A. This is nothing but Q by A, or you can say dQ by dA. Now, let us say the velocity at this point is V0 as given in the question. The velocity at somewhere at this point is V1. Will V1 be equal to V0, or V1 be greater than V0, or V1 be less than V0? Which case do you think is going to occur? Anyone? Bhavana, what do you think will happen?
The V1 is less than V0.
V1 is less than V0. Why do you think this is the case? Justify your answer. Okay, actually V1 should be greater than V0 because you're adding fluid through this porous region. So by the time the fluid reaches to this point, there will be more fluid flowing than the fluid which started initially. Is that clear? Why V1 should be greater than V0?
Yes, ma'am. I thought in the reverse way, ma'am. That's why I thought V1 is less than
Okay,
V0.
okay, okay, no problem. So now since we have a basic understanding of the question, we can proceed solving it. The way to solve these type of questions, so this is essentially a mass balance question, is you take a small section. So let us say at a distance x, consider a section of the pipe which has a differential thickness dx. Now, what is the area of this differential section? So at 3D representation will help you better. So this is our pipe. And I'm considering this portion. This portion, this entire circumferential portion as my dx. So what is this? What is the area of this dx? The area will be nothing but the perimeter
2 pi
multiplied
r.
by thickness. So 2 pi r dx. This will be our dA. Okay. So once you know dA, let us write the mass balance equation. What is the mass balance? So mass in should be is equal to mass out when there is no accumulation, which means that, so they have mentioned that the fluid is incompressible, which essentially means V in volumetric flow rate or Q in should be is equal to Q out. So if you consider this element, let us assume the velocity here is V, and the velocity going out is going to be V plus dV. And what is the flow rate at which fluid is being added? So we have calculated dA to be this. And we know that dq by dA is qx by L whole square. So dq will be q into x by L whole square times dA, which is q into x by L whole square times 2 pi r dx. So this thing is going to be dq. So this is going to be V into A and V plus dV into A. So because we are writing the volumetric flow rate. Now what is the area of cross section? The area of cross section is nothing but the uh, pi r square. So once you write the mass balance, we have VA plus dq, which is the volumetric flow rate in, should be is equal to V plus dA, sorry, V plus dV times A. So VA is going to get cancelled, which means you have dq is equal to adv. Or in other terms, dq by dv is equal to pi r square, because the area of cross section is pi r square. But you know that dq is q into x by L whole square 2 pi r, sorry, 2 pi capital R times dx is equal to pi r square times dv. So 1 pi and an r get cancelled. You have 2q into x by L whole square dx. So 2q by r into x by L whole square dx is equal to dv. Now you can integrate this. And what are going to be the limits of integration? So if you start from here, at x is equal to 0, the velocity is v naught. And in the question, they are asking us the velocity distribution at some place, at some distance x. So let us say at some distance x, the velocity is going to be v. Now if you perform an integration, you'll have 2q by r into x cube by 3l where the limits x cubed by 3L, where the limits of x range from 0 to x will be equal to v minus v naught. And from here you will have v is equal to v naught plus 2 by 3 2q by 3 RL x cube. Let us see whether we can find this answer anywhere. I think we made a mistake. Okay, there is also going to be an x square here. 2q by 2q, so 3L square. Please check if we have missed anything. So we need to have x 2 by 3 x cubed by L square. So we have 1 by 3 and we have 4 by 3. Okay, so
అంటే diameter అన్నమాట.
yeah, diameter కదా. Okay, so 4 by 3 అవుతుంది కదా.
Yes అన్న 4 by
4 by 3. Okay. సో ఈ ప్రాబ్లం అర్థమైందా? దిస్ ఈజ్ నథింగ్ బట్ డిఫరెన్షియల్ మాస్ బ్యాలెన్స్ అంటే ఇదే. Differential mass balance, which is nothing but you have taken a differential cross section and you performed a mass balance about it. Okay, let's try this problem. This is about momentum balance. So we have a plate and there is a support and a jet of water from a pipe is impinging onto the plate. And as soon as it strikes the plate, it is deflecting in this vertical directions. And the velocity of this jet is 20 meter per second. And the cross-sectional area of the jet is 0.01 meter square. Velocity of 20 meter per second strikes a plate and then flows parallel to it. And they're asking us to calculate Fx. What is the horizontal component of force? So take 2 minutes to try this problem. Okay. Did anyone try the problem? Any answers?
2000.
Right. 2000 వచ్చింది. Okay. So this is an example for macroscopic momentum balance. Macroscopic momentum balance. So the way to solve the problem is we construct a control volume. Once we construct the control volume, we know that summation F net. So sum of all forces acting on the fluid is equal to P dot out minus P dot in, which means the rate at which momentum leaves the control volume minus the rate at which momentum enters the control volume. So if we choose this to be the control volume, the rate at which momentum leaves the control volume, and by the way, this is the force balance in only x direction. Since momentum is a vector, we have to do a momentum balance for each and every direction. And in this particular case, this is for the x direction. So what are the net forces acting on the fluid? The net forces acting on the fluid are the force due to this solid. So the force exerted by the solid, let us say that is Fs. And Fs is equal to what is the rate at which momentum is exiting the control volume here. So the rate at which momentum exits is equal to mass flow rate into momentum. Sorry, mv into v. One second. So the rate at which momentum leaves is equal to m times mass flow rate times v. But we know that mass flow rate is rho va, which means Fs is going to be rho v square times a. So which is density is 10 power 3 and velocity is 400 and the area is 0.01, which gives us 4000 newtons. V square మిస్ చేసావా? I think 2000 వచ్చింది.
So V is equals to 20 కదమ్మా.
అవును, V is equal to 20. సో V స్క్వేర్ తీసుకోవాలి కదా, ఫోర్స్ కాబట్టి. ఫోర్స్ అంటే మాస్ ఫ్లో రేట్ ఇంటూ వెలాసిటీ. సో మాస్ ఫ్లో రేట్ అంటే ఇట్ ఈస్ rho VA. So Fs will be rho VA into V, which is rho V square A. అర్థమైందా?
Yes అన్న.
Okay. So let us look at a modification of the same problem. If we had a similar system, we had a support, but this time instead of a flat plate, we have a curved plate. We have a curved plate, and as soon as the fluid comes from the jet horizontally, the fluid is getting deflected back in the same direction. So, and everything else is same. So area is 0.01 meter square. The velocity is 20 meter per second. And also, yeah, the density is 1000. Can you tell me what Fx is going to be in this case? will the fx in both cases be same, or if they are different, what is the different value of fx? You can take a minute to think about this. Okay, so fx will not be equal to the fx in the previous case, because if you build a control volume now, near the solid surface we have two things near the curved surface. So the dotted line is the boundary of our control volume. We have momentum entering the control volume, and we also have momentum leaving the control volume. So the force is going to be the same formula, P out minus P in. In this case, the P out will remain the same. P out will be nothing but 4000, sorry, or rho V square A. But P in will be minus rho V square A in the opposite direction. As a result, the answer is going to be 2 rho V square A, or 8000 newtons. Is this clear? The modification of this question?
Yes, Amma.
Okay. So in the previous case, you could ask me, previous case lo momentum is leaving the control volume kada, ee direction lo, ila veltundi, ila veltundi. Then why didn't we include it in here? Or sorry, P out lo. P out lo E2 E2 ఎందుకు ఇంక్లూడ్ చేయలేదు? That is because they are leaving in a y direction. Y direction లో లీవ్ అవుతున్నాయి. Whereas మనం రాసిన ఫోర్స్ బ్యాలెన్స్ దేనికి? This is the for the x direction. So we don't have to, we should not consider that fluid which is leaving in the y direction. I hope that is clear to everyone. Okay. So that's all. Now we'll move into a new topic called flow past immersed bodies. So in flow past immersed bodies, we have mainly a couple of things. First thing is to understand drag force. And in drag force, we have two things. We need to understand the Stokes law and the Newton's law. And how do we apply them? When do we apply them? And then we have something called fluidization. And we also have boundary layer. Boundary layer. Usually this is for a flat plate. Okay, now let us look at drag force. What is drag? So whenever we have a solid placed in a flowing fluid, the force exerted by the fluid on the solid in the direction of flow is called drag force. So I'll repeat it again. The force exerted by the fluid on the solid in the direction of fluid flow is called drag force. So drag force may arise due to two reasons. One is because of tau W. Tau W is the wall shear. Or it may also arise due to fluid pressure, hydrostatic pressure P. So pressure. When drag occurs due to wall shear, it is called friction drag. When drag occurs due to pressure, it is called form drag. And one way to minimize form drag would be streamlining. For example, if you have two cars where this is one car and this is another car. The reason sports cars are designed in this sleek manner, streamlined manner, is because they minimize form drag. Thereby, the drag force will be reduced. So if the drag force is high, then the load on the engine is going to be very high. That is the reason. Now, how is this drag force quantified? So drag force is quantified using a drag coefficient. Drag coefficient is defined in this way. Drag coefficient is equal to Fd divided by half rho v bar square, where Fd is the drag force, rho is the density of the fluid, and v is the average fluid velocity. So in order to calculate Fd, Fd is nothing but half Cd rho v square. If you look carefully, this definition is analogous to friction factor, where friction factor is equal to tau w by half rho v bar square. But the difference is friction factor. This includes only skin friction, whereas this includes both skin friction as well as form friction, form drag. Oh, I'm sorry, I missed the term here. So this is Fd by A. Fd by A. You have Fd by A in the numerator. So this is going to be, Fd is going to be multiplied by AP. AP. Now AP stands for projected area. Projected area. Let us look what this projected area means. So if we have a sphere, and the fluid is flowing in this direction. So what is the area that is being projected to the fluid in its normal direction? That is going to be the projected area. So in order to calculate a projected area, you can think of it this way. So if this is the case where fluid is flowing in this direction, replace the fluid with light and place a screen behind the particle. So if this is light rays and you have a solid sphere and you have a screen over here, the shadow is going to be nothing but a circle. So the area of the circle is nothing but your projected area. Now let us look at another example. So let us say I have a cylinder and the cylinder is in this manner and the fluid is flowing in this manner. The diameter of the cylinder is D and the length is L. Can you tell me what is the AP? What is the projected area? Anyone? So it's the same thing. The projected area is going to be this area, pi by 4 d square. Now let us look at another case where we have fluid flowing in this way and the cylinder is oriented in this manner. Once again, diameter is d and length is L. Can you tell me what the AP is going to be? Anyone? AP is going to be LD. Is it clear why it is LD? Okay. So drag coefficient CD. CD is a function of the Reynolds number and the shape and orientation of the particle. So shape and orientation, what does this mean? This means if this is CD1 and in this case it is CD2, CD1 and CD2 are not going to be the same. They might be different. So because the orientation of the cylinder to the flow is different in both the cases. So this is about the CD. So there is a special case of okay, when there are spherical particles. For spherical particles, when the Reynolds number of the particle is less than 1. By the way, by Reynolds number of the particle, we mean density of the fluid into velocity of the particle, velocity of the particle with respect to the fluid into diameter of the particle divided by mu. This is the Reynolds number of particle. If Reynolds number of the spherical particle is less than 1, then it follows Stokes law. So Stokes law states that when you have a freely settling particle, at some point, so the drag force acting on the particle is 6 pi mu r v, where mu is the viscosity and v is the velocity, r is the radius of the particle, and the drag coefficient is given by 24 by nre. Both these expressions are analytically derived expressions. And it states that whenever, when a particle is falling down, when a particle is moving in a fluid in this direction, we have two forces acting on the particle. One force is the gravity, and the other force is the drag force. So this is a common case in physics. Whenever you have a constant force and a variable force, there exists certain velocity called terminal velocity, where the particle will no longer accelerate. That is, it will attain a constant velocity. So in case of Stokes law, the terminal velocity is does anyone remember? It is g dp square rho p minus rho divided by 18 mu. So if you look carefully, it varies with the square of the particle. It is proportional to the density difference, and it is inversely related to the viscosity of fluid. So these three things are very important, and you can have several questions on them. How the terminal velocity varies with density, diameter, and viscosity. And remember, this is valid when Reynolds number of the particle is less than 1. And if the Reynolds number of the particle is greater than 1000 and up to 2 into 10 power 5, there is another law called Newton's law. So in this Newton's law regime, the drag coefficient remains constant at 0.44. And the drag coefficient remains constant. And the velocity, the terminal velocity is given by 1.75 under root g dp into rho p minus rho root g dp rho p minus rho by rho. So it is very important to study these two equations in comparison. For example, in this equation, velocity varies with d square. In this equation, the velocity varies with d power half. And also look at the dependence on density. This equation is independent of viscosity. There is no viscosity term in this equation. The reason is because at high Reynolds number, the you no longer have viscosity dependence. You no longer have viscosity dependence. Inertial forces dominate. Inertial forces dominate. Therefore, you no longer have the viscous term. Whereas in low Reynolds number, viscous forces are important, hence you have the viscosity term. So, is everyone clear about these terminal velocity of settling and the Newton's law and the Stokes law? So there
Yes, Anna.
okay, so there are many problems available on this, and they are very simple problems, scoring problems. So I suggest you all to go through the problems. And then we have something called free settling and hindered settling. So free settling means that whenever you have particles settling in a fluid and the particles are sufficiently away from one another and also the walls of the container such that they don't have it is so this particle behaves as if it is the only particle falling down. It is not under the influence of any other particles or wall. That is called free settling. And the second case is when the particles are very close by or when the particles are near the wall. So the velocity gradients become complex and particles begin to influence each other. That is called hindered settling. That is called hindered settling. So hindered settling is usually observed in suspensions. And if the velocity of free settling is Vs, this velocity in suspensions is going to be V is equal to Vs into epsilon power n, where epsilon is the volume fraction of solids in the suspension. Epsilon is the volume fraction of solids in the suspension. And you can I suggest you go through McCabe and Smith for more discussion on free settling and hindered settling. There are some very important points in the theory. You can find them in McCabe and Smith. Now let us look at fluidization. So fluidization is a phenomena where you have a bed of particles. And you are sending in a fluid. If the velocity of the fluid is sufficiently high, such that the drag force created because of this flow is able to balance the mass, then you have fluidization. So the condition for fluidization is that the pressure drop across the bed, delta P, the delta P should balance the delta P should balance the weight of the particles. So I'll go through the fluidization given in the textbook. Okay, so this is about fluidization. And this is a very important graph. So as long as there is no fluidization, the bed height remains constant. And as soon as fluidization starts, the height of the bed goes on increasing as the superficial velocity, I'm sorry, as the superficial velocity keeps on increasing. And this is for the height of the bed. And when it comes to the pressure drop across the bed, so in a fixed bed, as the superficial velocity goes on increasing, the pressure drop keeps on increasing up to a point where the pressure drop equals the weight of the bed. The force due to the pressure drop equals the weight of the bed. Once that happens, even if you increase the velocity, the pressure drop is not going to increase. So this is a very important graph. Is everyone clear with this?
No.
Okay. Now there is something called minimum fluidization velocity. Minimum fluidization velocity, or okay, so let us look at this equation. Delta P is equal to G into 1 minus epsilon into rho P minus rho into L. This is the force balance equation. That is, when we say that the pressure drop should equal the weight of the bed per unit cross-section area, we obtain this equation. Delta P is G into 1 minus epsilon, where epsilon is the the volume fraction of solid particles. Rho P is the density of particles, and rho is the density of fluid, and L is the height of the bed. So, and this is the Ergon equation. Delta P by L is, which you need to memorize. Delta P by L is equal to 150 mu V naught by phi s square dp square into 1 minus epsilon square by epsilon cube. This first part is the viscous losses, and the second part is the inertial losses. So the total losses are going to be an summation. And if you look carefully, the viscous losses, you have a viscosity term, and they vary linearly with velocity. Whereas the inertial term, there is no viscosity dependence, and the pressure drop varies with the square of viscosity. And phi s is the sphericity. Sphericity. So let us see, how do we define sphericity? Sphericity, phi s is equal to 6 by dp divided by sp by vp. So what does this mean? This means this is the surface area to volume ratio of a sphere having a diameter of dp divided by the surface area to volume ratio of a particle having nominal size of dp. Nominal size of dp. So this is the definition of sphericity. So you can calculate the minimum fluidization velocity by equating these two. So delta P by L is actually this, but delta P by L should be this in order to balance the weight of the bed. And by solving for V, you'll get a quadratic equation which can be solved to obtain the VOM, which is the velocity for minimum fluidization velocity. And another important concept is that, so we have seen the basic equation is delta P is equal to delta P by L is equal to 1 minus epsilon times rho P minus rho times G. So how does epsilon vary with length of the bed? So as you can see, if everything else remains constant, we have L1 into 1 minus epsilon 1 is equal to L2 into 1 minus epsilon 2. So which is quite intuitively understandable, because let us say case 1, the bed, this is our bed, and epsilon 1, the fraction is epsilon 1, volume fraction of solids is void fraction is epsilon 1, and length is L. And in case 2, when you have increased the velocity further, the bed has expanded. So the length increased to L2. So the relationship between them is given by this. L1 into 1 minus epsilon 1 should be equal to L2 into 1 minus epsilon 2. Is everyone okay with fluidization? So if you want to know more about the derivation of the Ergon equation, you can refer to this part. Friction in flow through bed of solids. This is McCabe and Smith. This book is McCabe and Smith. So in this you have the derivation. And this equation, this entire equation is called the Ergon equation. The first part is called the Darcy equation, and the second part is called the, I think, Brooke-Plummer equation. Brooke-Plummer equation. So now let us try to solve a problem using what we have learned. Okay, let us try this problem. The data has been given. They have also given us the formula. They're asking us to calculate the minimum velocity of fluidization. So delta P by L is equal to 150 V bar mu by phi s square dp square into 1 minus epsilon whole square by epsilon cube plus 1.75 rho V naught square by phi s dp into 1 minus epsilon by epsilon cube. So all the data is given in the question. So they have given us the cross-sectional area. The area is known, 0.05 meters square. And we know the height. Height is nothing but L. L is given. L is 0.25 meters. And the porosity. The porosity of the bed epsilon. Epsilon is given as 0.35. And they have given us the density particles. Okay, they have given us the density of water. Density of water is 10 power 3. Viscosity has also been given, 10 power minus 3. And we know that at the condition for fluidization, delta P by L should be is equal to 1 minus epsilon into rho P minus rho into G. But did they give us information about velocity of the... okay, the density of particles has also been given. Diameter of the particle is 0.01 meters and the density of the particles is 2600 kg per meter cube. So once you equate this term to this term, let us see what are the unknowns here. We know mu, we know epsilon, we know phi s. Phi s is 1 because it's a sphere. We know dp, we know epsilon, we know rho, we know dp, we know epsilon, we know epsilon, we know rho p, we know rho, we know g. The only unknowns we have are v naught square and v. So by the way, these both are the same variable, v bar, or I'll also replace this by v bar square. So essentially you have a quadratic equation in v. If you solve this equation, you'll get the VOM bar, which is the minimum velocity of fluidization. Is this clear to everyone?
Anna.
Okay. Let us look at one more problem. Which is based on the Kozeny-Kármán equation. So the Kozeny-Kármán equation is delta P by L is equal to 150 V bar mu by phi s square dp square into 1 minus epsilon square by epsilon cube. This is the Kozeny-KC equation, Kozeny-Kármán equation. So air flows through a packed bed of a powdery material 1 centimeter depth. 1 centimeter depth means the L is 1 centimeter. And gas velocity V bar is 1 centimeter per second. And epsilon, they have said that the bed has a porosity of 0.4. And they have given us the density of the fluid. They have given us the viscosity of the fluid, which is air. And they have also, yeah, that's all. They have said the delta P. Delta P is equal to 1 centimeter of water. So 1 centimeter of water, which means you need to multiply, you need to calculate the delta P in Pascal units by doing rho GH, where rho is the density of water, G is 9.81 and H is 1 centimeter. So you also know delta P. Once you know delta P, look at the equation. You know delta P, you know L, you know V bar. Mu has been given. Phi S, they have not given us phi S. So we can assume that the particle is spherical. Phi S is 1. You don't know dp. You don't know dp. You know epsilon. So you can calculate dp. That is going to give you an estimate of the particle size of the powder. So is this clear to everyone?
Anna.
Okay. Okay then. That's it for today. Thank you everyone.
Anna.